As promised, we're now going to build circuitry for doing 4-bit addition. So we're going to take two 4-bit numbers and we are going to add them in the same way that we did in the previous lecture. We just stack them on top of each other. We sum, we carry, we sum, we carry, we sum, and we keep going, and we do binary arithmetic or addition. And obviously, we're going to use the 1-bit adder that we just built because we know that n-bit addition is just a series of these 1-bit additions, so we're going to build them. We're going to build this in a smart way. All right, so please build for me a circuit that adds two 4-bit numbers. And again, I want to emphasize, pay attention to the bits because the inputs is not 2. It's now, well, at least 8, but we know we have all those carries too, right? So we always have to be thinking in terms of bit representations because everything we do operates on bits. All right, well, we know how to do 1-bit addition. So notice here I've done something very similar to what I did with the 1-bit compare for equality. I've taken that full circuitry that I showed you in the previous lecture. I've got digits. I have the carry in, that's what's coming in from the previous column. And I have two outputs, the sum, what drops down below, and the carry out, what carries over, okay? So 3 in, 2 out, and now I've simply drawn a little box and I've written 1 add, which is a 1-bit addition, and that is that full circuitry. And again, this is the power of abstraction. Once I know what's in here, the same way that I know what's inside of a gate, I simply can draw it in this abstract way, and I don't have to worry about it anymore. I've built it, I've tested it, I know it works, and now I can simply use it. And so now what we want to do is wire up a bunch of these things in order to do 4-bit addition. And of course we could do 6, 8, etc., etc. We'll stop at 4 because I think you'll get the point. So let's start thinking about how we want that to work. And you just got to think about how does it work. I take these two things carry in, and then I'm going to shove that next carry to the next one, which should be the input to the next 1-bit adder, and we keep repeating that over and over again. So let's see how that works. All right, so first of all, here are my 4 bits for A and my 4 bits for B. So that's what I want to sum up. Got those carries I've got to bring in. That's fine. We'll do that in a minute. Here's my 1-bit addition right here. Here are my two outputs. There's a carry, and then there's the digit, the sum. Notice, by the way, that this is the thing that's coming out. This carry is for internal purposes. I don't report that to the summation. I just need that to propagate the bits down. So the output outside the circuitry is here. Now, okay, so here's A0, here's B0. Those are the two ins, but I also need a carry in. So what's the carry in for the rightmost bit? Well, it's 0. Okay, good. So we just shove a 0 in there. That's fine. That's easy to do. So now I've got 3 in. I'm going to get a carry, which, again, internal purposes is going to be used for the next bit, A1 and B1. And the output is really just D0. That's the only thing I care about. That will actually come out. All right, so how do we add the next one? Well, I want to take A1 and B1, and what is the carry in? It was the carry out from the previous bit. So that's simply going to go into the 1-bit adder. Good. So I've got A1 here. Again, cross wires, open circle. Here comes B1 right here. The carry came in from above this adder. The output is the same, D1, and now I've got the next carry. Good. Now we see the pattern. Right? Started with a carry of 0, and we keep dropping it down, shoving it into the adder associated with the column that is to our left. All right, good. A2, here it is, cross wire into the adder. Here is B2, into the adder, carry in, carry out. My next sum is right there. And now we're almost home. We got the last one right here, and we got the last sum. What do I do with the carry out? Well, I can only have 4 outputs. That's how I've designed it. So I have 4 in and 4 out. So if these two things sum up to something that is bigger than 4 bits, I'm going to have what's called an overflow, and for now I'm going to ignore it. There's other ways of dealing with this which we won't get into. I fifth output and summed and said I have 4 in, 2 4-bit numbers, and please allow me to have an overflow, but I'm going to ignore that. So that carry just goes into junk and gets ignored. Okay? So notice again the power of abstraction. Notice how much easier this was to do once we understood we had this building block here. It's a lot like functions. Once you build these simple functions that have functionality, you can use them over and over again to build more and more and more complex things. Okay? And of course I can take 2 4-bit adders now and make an 8-bit adder. And then I can take 2 8-bit adders, make a 16-bit adder. And each time I can keep abstracting out the complexity of what's underneath it. All right, so this again is the circuitry for a 1-bit adder, and if you remember in the last lecture I said that's a lot of gates to do something as simple as a 1-bit adder. I just want to sort of run through a little back of the envelope calculation with you here. Imagine I'm trying to build a 32-bit adder. That's a reasonably, allows you to represent reasonably large numbers. Well then what I would need are 96 NOT gates, 512 AND gates, and 192 OR gates. How did I get to that? Well, this thing over here for the 1-bit has 6 OR gates, 16 AND gates, and 3 NOT gates. Okay? And so I just multiplied that by 32 each. So I have 800 gates to do only addition, right? Multiplication, division, all those things can't be done. So is that a lot? Is 800 gates a lot? Well, that 800 gates corresponds to about 1,500 transistors, because when you're building circuitry, you're building gates, but really underneath it, it's transistors, right? So now look at what I'm doing. I'm popping out the levels of abstraction. I'm pushing through the 1-bits. I've got the circuitry for the 32-bit adder. That's made up of a bunch of 1-bit adders. That's made up of a bunch of gates, and that's made up of a bunch of transistors. I need 1,500 transistors to do one single mathematical operation, which is 32-bit addition. Now, if we were in 1945, I would need roughly a refrigerator-sized computer to do that single calculation. That's insane. And that's because transistors were not these tiny minuscule things we have today. They were big physical things that occupied a lot of space. So the magic in today's computers that if I have, for 1,500 transistors, I can put that on something that is much smaller than a printed period on a piece of paper. This is the magic of modern day computers, that these transistors can now be made incredibly small. And so you can pack more and more transistors onto a circuit board, which means you can pack more gates, which means you can pack more circuitry, which means you can have now in your jacket pocket a cell phone that is the equivalent of a supercomputer from 60 years ago. And so this is, what's sort of amazing about this to me when you do these calculations is you see the complexity of a modern computer. All we've done is built addition, not even a calculator, and look at how much work we've had to done, but look at the power of these tiny transistors. Okay? All right, so in the next 2 lectures, these are the last 2, we're going to talk a little bit more about circuitry. We're going to talk about optimization. How do you make these things, because of how big they can get? If you do this sort of very simple design, you may end up with prohibitively large circuitry, and there's some smart things that you can do, and I'm going to give you a couple of examples of that just to sort of round out the circuit design here. All right, see you in a few minutes.